All right, so let's go to the lab for a second here. Typically, the way we characterize these constitutive models is we use the uniaxial tension test, right? Or compression, either one. So we go to the lab and we either push or pull on a sample, a typically cylindrical sample. We measure the change in length from some maybe extensiometer or strain gauge that we place on the sample. If the sample is metal, sometimes we'll use a sample that looks like so-called dog bone. So it'll look like this. We put that in a standard test frame and push or pull on it, and we measure the strain, we measure the force, and that's how we come up with our stress strain laws. And in one dimension, we'll measure something that looks like this. And so the slope of this is the Young's modulus, like we talked about. And so if we were to go, say we're talking about a metal for a second, if we have a large plate, let's say rolled steel or something, if we were to then cut these dog bone samples from the plate, giving a bunch of different orientations, like this. So if we were to cut these samples from the plate at every given orientation and conduct this tensile test every time, then we'd actually, you'd have you'd have a Young's modulus corresponding to sort of every direction that you cut it from, and that would allow you to, if you did enough of them, to populate the entire constitutive tensor. But of course, steel is a fairly homogeneous material. It's fairly isotropic. So in reality, you wouldn't measure much difference in those E's for the different given sample layups. And so you'd realize this is an isotropic material. But this is one hypothetical way in which you can measure the different material constants. Okay? But the problem is everything we covered up to right now assumes that the material is elastic. Well, to how much strain is most material elastic? Just like a steel, maybe. More like 0.2%. So a fraction of 1% strain, and the material is no longer going to be elastic. Right? And so if this is in fact a steel, what you'd see is if I continued to strain it, I'd get into a region like this. And we call this so-called plasticity or inelasticity. Okay? And we call it plasticity or inelasticity because any strain beyond this point, and this is called the yield point, any strain beyond this point, the yield point, is permanent. Right? So if I strain it past this point and then I stop and I unload it, it'll unload elastically. So it'll unload along the same slope as its initial elastic loading. It'll unload elastically, and up to this point, there'll be some permanent strain, or maybe we call some plastic strain left in the material. And we all know this. I mean, anybody's who played with a paper clip, right? If you just pluck the end of a paper clip lightly, it always goes back to its original position. But eventually, if you pull it too far, then it doesn't go back, right? You've plastically deformed it, the paper clip. Right? So. And of course, the actual shape of what the curve looks like beyond the yield point is different for all materials. So like for example, an annealed copper would have a fairly flat part right here. Most steels exhibit some type of work hardening, so they're gonna have some kind of. The more I strain it, they're gonna appear to get harder and harder. Okay. So this course is a course on geomechanics. So let's talk about rocks. Is a rock plastic? Does it deform plastically? Or inelastically? Yeah, it's sort of a trick question. So if I go to the lab and I just perform one of these unconfined compressive strength tests, if I just go and take my little rock sample and I press on it, well, the rock's going to split down the middle and it's going to fail. And if I look at the stress-strain curve, it's just going to look like this, right? However, if I apply a confining pressure to it, right? So if I confine it, and the way we do these in the laboratory is we actually, the sample itself is placed inside some type of confining fluid, hydraulic fluid, and so that hydraulic fluid is then taken up to very high pressures, and then it's mechanically loaded from the ends, okay? These are called hydrostatic compression tests. And of course, most rocks are also porous materials, so there's typically, you have to do these experiments very carefully. We sleeve the material or put it inside a membrane so that the hydraulic fluid from the outside doesn't permeate the sample, right? We want to protect that. And sometimes we even want to flow fluid through it and so that we control the pore pressure inside the sample. We'll talk about pore pressure and pore elasticity real soon. But sometimes we want to control the pressure inside the sample independently due to the presence of some pore fluid, okay? But when we do these, so we'll typically do these, they're called Tri-Axial compression tests. And in this case, since the sample is confined equally on all sides, then if you look at the principal stresses, the second and the third principal stresses are equal to some value, say the stress that you confine it with, and then you control the first principal stress independently. Okay, and so if you do that and then you go to the lab, what you'll get is a family of stress-strain curves that are a function of then the confining pressure. So you will see some inelasticity, and the shape of the curve will be a function of the confining pressure. Right? So typically, as you increase the confining pressure, the rock will tend to behave in a stronger manner. Okay, but kind of ran out of space up there. A typical stress-strain curve for a rock will have an elastic portion. It'll have some inelasticity, and then typically you'll see something like this. So what this sort of softening effect comes from is from pore collapse. So if you continue to squeeze the rock, you're eventually going to collapse the pores that are in it, and you'll get some softening effect in the stress-strain curve due to that. And so just to sort of give you a picture that's not just a cartoon, I'll show you some real data. So this is some real experimental data that I took when I was at Sandia on two different types of concrete, which is called conventional strength concrete and high strength concrete. So that's the two curves, and these are a function these are at 58 KSI confining pressure, and so the way this is actually axial engineering strain. Remember, I got onto you in the first day of class about labeling your strain, and I didn't do it. But this is actually actual engineering strain, and then you notice on the side it's plotted as principal stress difference. And again, the reason for that it's plotted that way, remember, if we look at Moore's circle, remember sigma 2 and sigma 3 are equal, so we just have one circle. that's like sigma 1, and then this point is sigma 2 equals sigma 3. And if you remember, on the Moore circle, this guy right here is like tau max, right? So the distance sigma 1 minus sigma 2 is 2 tau max, right? So 2 tau max is sigma 1 minus sigma 2, or sigma 3, either one. And so that's really what you're looking at over here on this axis is sort of 2 tau max. So it's a measure of the shear strength of the material, right? Shear strength versus axial strain. And so you see in this case quite a bit of inelastic flow. In fact, you can't really see any elasticity at all. It's really small, right? So the elastic range is really small. And this is not actually failure. This is just unloading. So it was taken out to almost 15% strain and then unloaded. And now this is concrete. Concrete's not technically a rock, right? But we categorize it with geomaterials. So rocks, concrete, soils. Characteristically, it behaves similar to a rock. And you can almost never get the right elastic modulus on the initial loading of any kind of geomaterial because you have these small little flaws and other gaps in the material that are taken up when you initially confine it. So you have a little bit of slip on the planes, on the little cracks and micro flaws and everything that are in the rock. So you can almost never get the right elastic modulus on the initial loading. So we usually don't even try. Usually what you get it from is on unloading cycle. So a lot of times when you look at these geomaterials, stress strain curves, you'll see stress strain curve, and you'll see these little, what those are, load unload cycles, and they're so that you can get the elastic modulus of the material. So excuse me. So this was at 58 KSI confining pressure, and if you drop down to 29 KSI, you can see a pretty significant difference. So you notice the material is sort of at a maximum strength here is somewhere shear strength, and somewhere like around 55, somewhere around 55 PSI, 55,000 PSI. Whereas here, it's 70, 80, 90. You also see a larger gap between the two concretes in this case. The high strength concrete is much stronger at higher confining pressure than it is at the lower confining pressure. So that's some real data. Here you don't see, well, it wasn't strained out far enough, I guess, but you don't see the pore collapse and other things. But if you continue to strain it or take it to high enough confining pressures, you can definitely see that. So